because I have a student, as you know, the Sadaf Habibi, and she entered this graduate school via English course. And all students who entered this graduate school via English course is supposed to study mathematics just by using English. So I decided to give my talk here in English. So please allow me. And also, first of all, I'd like to thank all organizers and all colleagues for giving me a chance to talk here. I think that this is my second opportunity to talk here. The first one was 2005, October 2005. Just I was employed by Osaka City University as an associate professor. So almost 70 years ago, almost all colleagues are new, except for Onita Sensei, I think. And now I'm very nervous and stressful because I speak English in front of you, and the only exception is Habibi. So all are Japanese. But anyway, let me start my talk. Today I talk about some nonlinear partial differential equations, and which is driven by some Finsler Laplacian, which is an isotropic differential operator, and also quasi-linear type operator. And the nonlinearity is very simple. And maybe you may think that the form is very simple nonlinear PDE, but it is very, for me, it is very interesting because this kind of problem is not so well studied. So we started with Habibi like this. Okay, first introduction. Okay, I believe that the most important differential operator is Laplacian. Of course, now X is a point in n-dimensional Euclidean space, and U is a function from Rn to R. And of course, everybody knows that the Laplacian U of X is the summation of I is equal to 1 to n, the second derivative with respect to xi, dxi square is this one. And this is very homogeneous and very, in some sense, this operator doesn't have any special direction because this operator takes derivatives to all directions xi for I is equal to 1 to n. So this is a isotropic differential operator in some sense. And also this has a divergence structure. This can be written by divergence gradient U of x. Here, of course, gradient U of x is equal to a vector round U round x1. Every student must study this kind of notion in vector analysis in second grade or third grade round xn. This one. This is divergence gradient. And now, if we introduce, modulus of x is a Euclidean norm. This is very usual norm. X1 square plus xn square. We take a summation and take 1/2 here. Euclidean norm. Then we can calculate very easily is like this, modulus of x, x over x, this one. Therefore, we can written like this. Laplacian U is equal to divergence gradient to U, but we take grad to U, nabla U, grad to U over modulus of grad to U. We can write like this. Then we proceed furthermore. Nabla U. Here is, for example, modulus of Cauchy. We take a derivative with respect to Cauchy, and we insert cushy as grad u x. So we can write the Laplacian like this. So more generally, for any q, okay, q is equal to 1 is okay. Q is between 1 and infinity. We introduce a q Laplacian. Laplace q u is like this, divergence nabla u to the power q minus q grad u. Again, this operator can be written divergence nabla u to the power q minus 1. Gradient cushy, modulus of cushy, and after taking derivative, we put cushy is equal to gradient u, like this. This is called the q Laplace operator, or q Laplacian. This is a typical Kessler linear type operator, this one. And now we use this Euclidean norm, this one. So if we change the norm, because we have many norms in the Euclidean space, then if we change from Euclidean norm to any other norm, then what happens? So we are interested in such topics. So we want to change Euclidean norm to any norm. We like H. Now, norm must satisfy some axiom of norms of non-negativity and positively homogeneous, homogeneity, and also non-negativity. Okay, I should write for H cushy. Now, the cushy is a vector in Rn. This is called a norm. Of course, everyone knows that H cushy non-negativity. H cushy is non-negative, and H cushy is equal to 0, is equivalent to cushy is a 0 vector, and H mod T times cushy is, this is positively one homogeneity, H cushy for any T in R and cushy in Rn, and triangle inequality. H cushy plus eta must be bounded by H cushy plus H eta. And also, we assume, moreover, assume that some regularity, we assume that H is C2 Rn minus 0, minus the origin, and also convexity. Convexity means that Hessian of H square, this one, this is a symmetric matrix, is positive definite. This is a strictly convexity. We assume here. And by using this general norm, we can obtain several geometric notions. Okay. First, if we are given some norm, then we can define the dual norm. H naught X is defined like this: Supremum in Rn, such that this is an inner product. Cushy and X. We take an inner product in Rn and divide it by H cushy. This is dual norm. And it is known that if H is strictly convex, then H naught is also strictly convex norm. And this set, by using the dual norm, we define this set, H naught unit ball. That means that H, for any x such that H naught x is less than 1. This is called the H naught unit ball, or more popularly, this is called the Wolf ball. This is a kind of unit ball in this general setting. And we can define the H perimeter for any Borel set. We can define PHE. This is the perimeter. It is a generalization of the surface area of some set E. PHE is defined like this: Supremum integral E divergence sigma dx. Here, sigma is a support compact smooth function, vector function, which takes value in Rn, such that H naught sigma x is less than or equal to 1. This is called the anisotropic or anisotropic H perimeter. This one. Then, for example, by using these geometric notions, we know the famous Wolf theorem or Finsler isoperimeter inequalities like this. Okay. Now we are working on with this kind of general norm. And sometimes this kind of norm is called the Finsler norm because the whole Euclidean space with this general norm is the most simplest. It is the simplest example of the Finsler manifold. This is sometimes called the Minkowski manifold or something like that. But anyway, Euclidean space with this norm is the simplest example of the Finsler manifold. And now we want to study some nonlinear elliptic PDE on this kind of simplest Finsler manifold. But anyway, Wolf theorem. Incidentally, Wolf is not a mathematician. I think that he is a physicist, and he studies some kind of solid physics or something like that. And he studied crystals. And Wolf theorem says that, so anyway, E is a Borel set. Any Borel set. Then this holds true. Finsler anisotropic H perimeter divided by this one is a volume of 2 to the power, this one, n over n minus 1 is greater than or equal to Wolf ball n minus 1 over n PHW. W is a Wolf ball. And this is actually can be calculated n kappa n 2 over 1 over n. Kappa n is a volume of Wolf ball. This is called the anisotropic or Finsler isoperimetric inequality. Actually, if we have isoperimetric inequality, then we can derive from the isoperimetric inequality that Sobolev inequalities or Schrödinger-Mozart inequalities or other inequalities. And this is a mother of all interested inequalities. But we can get this kind of isomorphic inequality. Also, the equality holds. Equality holds if and only if E has a Wolf shape. This means that E is a translation or a dilation of the Wolf ball. E has a Wolf shape. This is true. And finally, I want to introduce Finsler Laplacian. Before I introduce the Q Laplacian, Q Laplace operator, but in this talk, Q must be equal to the dimension, capital N. Therefore, I want to introduce Finsler N Laplacian, QNU. QNU of X is equal. This is again the divergence form operator. Divergence and H, gradient U to the power N minus 1. And we take a derivative with respect to H, Laplace H. And after taking a derivative, we insert Cushy is equal to gradient of UX. This is called the Finsler N Laplacian. So if you imagine that H Cushy is a modulus of Cushy, that means that H Cushy is a Euclidean norm, then this QNU coincides with the usual N Laplace operator. But now we take general norm. So this is anisotropic differential operator because okay, I forgot to mention that the H Cushy example of H Cushy. For example, Cushy is a vector, Cushy1, Cushy H Cushy is the small LP norm, Cushy1 to the power P plus Cushy2 modulus. We take to the power P, Cushy to the power P, and we take 1 over P exponent. This one. This, if we take this kind of, this is also norm on the Euclidean space. And in this case, we can calculate QNU more explicitly. But anyway, P is two cases a Euclidean. And the Euclidean ball is just a ball. This one, C is equal to 1. But for example, P is equal to 1. P is equal to 1 case. This one. This is P is equal to 1 case. And maybe P is equal to 3 or P is equal to 4 or much more general one is. Again, the Wolf ball is, this kind of ball is convex, but the shape is different. And for example, this has some special direction with respect to this norm. So our general question is like this. From now on, we consider some nonlinear differential equations, and our general question is like this. How does the anisotropy described by the norm H affect on the blow-up behavior of solutions to some nonlinear PDE. This is the first our vague question. So we want to quantify or qualify the effect of the anisotropy of the differential operator. Okay. And then we consider much more precisely our problem. I want to introduce the Finsler Lane-Emden problem in n-dimensional bounded domain. Okay, in the following, let omega is the bounded domain, bounded open set in Rn. And from now on, P is the nonlinear exponent, and P is between 1 and half for any P. And let's consider the following nonlinear elliptic PD, which is the main part is N Laplacian. Finsler N Laplacian minus QNU is equal to U to the power P in omega. And we are interested in the positive solution. U is positive in omega. Subject to the Dirichlet boundary condition. U is equal to on the boundary of omega. And this problem is called the Finsler Lane-Emden problem because, for example, this n equal 2 case and Qn is, in this case, Qn is and n equal 2 case, and if HC is a Euclidean norm, then this is just a Laplacian. Minus Laplace U is equal to U to the power P. This simple looking problem is okay. Concerning this kind of problem, there are many results, but we don't know whole solution structures, even for this case. Even this is Laplacian case is not known. Therefore, this is very this kind of problem has a rich structure, and I'm interested in this kind of problem. And now we want to find that the solution is in the W1N Sobolev space, W1N 0 omega. This is a symbol of Sobolev space, and which means that the first order distributional derivative is nth power integral. So we can take a derivative with respect to x, so gradient u, and modulus of gradient u to the power n is integral. And u is equal to 0 on the boundary, this one. This is a problem. And concerning the existence of at least one solution, it is not so difficult because of the Sobolev compact embedding of the Sobolev, which means that if we consider the constraint variational problem and the minimization problem, so let's define CP is like this. Infman, we want to minimize this energy function. This is a generalized Dirichlet functional, h grad u to the power n dx. Subject to this condition, u is a function in W1N 0 omega, and satisfies this additional constraint, this one. Then, as I said to you before, that W1N0, okay. Sobolev embedding, which means that some Sobolev space must be embedded in some Lebesgue space. And such embedding with compact is a very important fact in some cases. And in this case also, W1N0 omega embedded for any Q, LQ omega, Q finite is open. Unfortunately, the function in W1N0 omega may not be bounded. Therefore, W1N0 omega cannot be embedded in L infinity omega, but in this case, the dimension omega and the integrability n is n coincide. In this case, W1N0 omega can be embedded for any Lebesgue space, integral space, LQ omega, for any Q finite. And also, the embedding is compact. Compact embedding, which means that the identity map is compact operator, compact. And by using this compactness, we can get at least one minimizer. This fact implies that there exists at least one minimizer, which I denote U bar P in W1P 0 omega, such that this one must satisfy this constraint, and Cp is equal to integral omega. So this is a minimizer gradient of U bar P to the power n dx. This one. And if we put new function UPX is Cp to the power P plus 1 minus n, 1 over P plus 1 minus n, U bar P, then UP is a solution of our problem, solution to P. And this solution is obtained by using the minimizer. So we call this one the least energy solution. UP is called the least energy solution. From now on, I want to abbreviate LSE, least energy, LES, least energy solution, LES, this one. This is a solution to P. Maybe we have much more solutions, but this solution is in some sense very easy to obtain. Just we use the compactness of the Sobolev embedding. So this is very easy. In some sense, this is very natural solution. So I want to know everything about this kind of least energy solution, because this is very, very easy to obtain. And
excuse me, but
yes.
This U bar P is not unique.
Not unique. This is a very big problem. Even for the N Laplacian case, the uniqueness is not known. N equal 2 case, and the norm is a Euclidean norm case. The two-dimensional case, uniqueness is known by Chancelin's result in 1994. But basically, we don't know the uniqueness. It's a very big problem. Thank you very much.
So, but you take one solution.
One solution, yes. One solution. So maybe we have several minimizer, but I believe that the uniqueness. But anyway, we have at least one solution if we can get. So our question is like this. What happens to UP if P goes to plus infinity? Because Sobolev embedding is valid for any Q finite. Therefore, we can take a limit as P goes to infinity. So this problem contains one parameter. This is a nonlinear exponent P. We can move P as a parameter. And what happens to UP if P tends to infinity? This one. And the following, we will show, I want to show you several results. And these results are contained in a paper with Habibi and me. And you can see from OCAMI preprint series or archive. The first one is like this. Let UP for any P greater than 1 be state energy solutions. Then there exists some positive constant C1, C2, such that in the L infinity norm, so maximum norm, UP doesn't vanish or doesn't blow up. This is independent of P. Such that for P large, this means that in the L infinity norm, if we see the solution shape, that solution doesn't vanish to 0 or doesn't go to plus infinity. So in some sense, concerning on UP, we don't have a blow up phenomena. This one. Now, furthermore, we have several asymptotic formula. For limit P tends to infinity, P to the power n minus 1, integral omega h grad u to the power n dx. This limit exists and coincides with the P to the power n minus 1, integral omega up to the power P plus 1. Yes. Now UP is positive, so we don't need to take modulus. And this one is equal to n over n minus 1, E and beta n to the power n minus 1. Here, beta n is n times PHW. PHW is a Wolf ball, and anisotropic H perimeter of that Wolf ball to the power 1 over n minus 1. Actually, this one is n kappa n 1 over n minus 1. This is a best constant, best exponent of the Finsler Turning-Amazon inequality. Anyway, we can obtain this asymptotic formula. This one. E is a Napier number. This is the first theorem. And the second theorem is like this. Again, UP, least energy solution. Least energy solution. Then we get limit soup P tends to infinity UP to the L infinity omega. This is bounded with independent of P from below and from above. And we take a limit soup. Then this is bounded by e to the power n over n minus 1. No. N minus 1 over n. This one, yes. This is true. And actually the lower bound is easy to obtain. The upper bound, this one, this part is, I believe this part is new, even for the Euclidean norm case. New even for H cushy is a modulus cushy. Means that our Finsler N Laplacian Qn is just a usual N Laplacian case. Even for this case, this estimate is new. And we believe that maybe this equality holds true, but we cannot prove up to now. And theorem 3, in order to state the theorem 3 put, we want to define several notions. Put Vp, new function Vpx is equal to Upx. This is the least energy solution divided by integral omega Up to the power P and 1 over n minus 1. This one. Then Vp satisfies this elliptic equation minus Qn Vp is equal to Up to the power P divided by integral of Up to the power P dx. This one. Maybe we write this one, Fpx in omega. And of course, Vp is positive function, and Vp is subject to the Differential boundary condition. This is the equation of Vp, new function Vp. And we can see that the denominator goes to 0 as P goes to infinity. Therefore, Up is bounded from below and above. Vp goes to plus infinity as P goes to infinity. So in this function, the Vp exhibits some blow-up behavior. And also, we want to define S blow-up set. S is a set of points x in omega bar such that there exists some point, interior point in omega, and there exists some Pn. Pn goes to plus infinity as n goes to infinity, such that Upn xn, xn goes to x, and Vpn xn goes to plus infinity. This set is called the blow-up set. Blow-up set of solution sequence of Vp. This one. And our theorem 3 states like this. Again, let Up a least energy solution. Then this interior blow-up point. S is a set of points in omega closure. But if we consider only the interior point, S intersection of omega, then this is finite. This is a set of points, and the number of set of points And this cardinality is finite. Actually, we should. There exists some constant dn, which is depending on just only zero dimension capital N. And this dn is between 0 and 1, such that cardinality of S intersection omega is less than or equal to e to the power n minus 1 over n. No. Okay. N minus 1 over n divided by dn. And this is Gauss symbol. This estimate holds true. And also, so the interior blow-up point is finite. And if they assume S intersection omega is like this, x1 and x2, so k point blow-up. K point interior blow-up. Then we have FP. We recall that FPX is UP to the power P x divided by integral omega UP to the power PX dx. So this is, if we integrated this function FPX with respect to x on omega, then the L1 norm of FPX is equal to 1. Therefore, in some, this is a probability measure, unit measure. And this measure, if we take a limit, p goes to infinity, then in the sense of radon measure, this goes to finite sum of Dirac mass, supported of xi. I is equal to 1 to k. Delta xi, Dirac delta. And this gamma I is a positive, and the sum of gamma I, we cannot say that the total mass is equal to 1, but just we get the weaker estimate. But anyway, this function goes to some summation of the Dirac masses. This is in the broad sense. This kind of phenomena is described by the Pierre-Louis-Lyon's concentration compactness argument, and which by this theory, Pierre got Fields Medal in 1994. Anyway, this kind of phenomena is very, since then, this kind of phenomena is very studied, well studied, but there are many open problems, still open. Many problems still open. But anyway, we can get this one. And finally, Theorem 4. Theorem 4 says that boundary blow, one-point boundary blow-up cannot occur. Which says that assume S, sharp S is equal to 1, and S equal x naught. And x naught is by definition, S is a set of points in the closure of omega bar. Then we get, actually x0 is in omega, interior point. So the one point blow up set cannot locate on the boundary of omega. This is a theorem 4. And actually, this kind of problem for Euclidean norm is studied by Junqian Wei and Sadaf Lane in 1994, 1995, 1996. They have several a series of papers, but and we follow their argument. But in some part, we have to develop some new argument. And okay, in the rest of my time, I will show a part of the theorem. I want to show some flavor of blow-up analysis around this problem. The proof of this fact is new, even for the Euclidean norm case. Therefore, I want to show you. Infinity norm of UP is bounded by e to the power n minus 1 over n. I want to prove here this one. And we follow the argument of adjacency and Gross's argument. Massimo Grossi's. This is in 1990. And let XP is a maximum point of the least energy solution. Of UP. That means UPXP is equal to the N infinity norm of UP. At least 1 point. There is at least 1 point, this one. And we introduce a new function, ZP. ZPX is equal to like this. P divided by UPXP. UP epsilon px times xp minus UPXP. This is a new function. And here x is a set of points, omega p. Omega p is translated by xp and scaled by 1 over epsilon p. This one. And what is epsilon p? Epsilon p is the scaling parameter. And epsilon p is a scaling parameter. This is the definition. Epsilon p to the power n, p to the power n minus 1, UPXP p plus 1 minus n. This is equal to 1. This is the definition of epsilon p. This one. Then, if we introduce this kind of new function, then ZP, okay, first of all, I want to write now this is a bounded domain, omega in Rn, and this is xp. Maybe UP is a function like this. The maximum point of UP is xp, and we translate xp and we scale. Actually, we think that the p goes to plus infinity. Sorry, this is UPXP. UPXP is bounded from below. Therefore, epsilon p must go to 0 as p goes to infinity. So like this. This is the same. And xp goes to 0. This is omega p divided by epsilon p. So if this is large order 1, then this is large order 1 over epsilon p. And we can check that if p goes to infinity, the limit set of omega p is Rn, whole space Rn, or half space Rn plus. We can check this one. And now the ZP is like this. Actually, we subtract the maximum point UPXP, maximum value. That's why ZP must be non-positive. Then ZP satisfies like this, minus Qn. ZP is equal to 1 plus ZP over P to the power P plus 1 in omega P. And ZP is negative. And ZP on the boundary, here is 0. Therefore, UPXP, this one, ZP is equal to minus P. Minus P, and ZP 0. This is the maximum point. And this is equal to 0. Is satisfied. And the trick is like this. Actually, by using the Harnack inequality, because our differential operator is Kessler linear, so we can appeal to the Harnack inequality. Then by using the Harnack inequality, we can get some uniform bound of the gradient. Then we can get equicontinuity and uniform boundedness. So we can use the Ascoli-Alcala theorem. So anyway, we have to go to some subsequence, but by using subsequence, there is some function z as p tends to infinity in C1 local, Rn or C1 Rn plus. So C1 local Rn or Rn plus. By using the Harnack inequality. And this is a high school mathematics. 1 plus P over ZP to the power P plus 1 goes to E to the power Z. So nonlinearity changes like this. This one. Therefore, the limit function satisfies this kind of Liouville type theorem, Liouville type equation minus Qnz is equal to E to the power Z. And we can get that Z is a negative function and the integral is Z. This is finite. We can check that. This is Rn or Rn plus. This is Liouville function, Liouville type theorem, Liouville type elliptic PDE. And if n equal to two-dimensional case, and this operator is a Laplacian case, we have a complete classification of all solutions. But unfortunately, in this general case, we don't know the all solutions. We don't have classification of solutions. So this is a difficult point. But fortunately, we can get some estimate from this function, but for this function. Maybe. Yeah. This is lemma. This function, we estimate like this, integral Rn or Rn plus is also okay. E to the power Z dx is bounded from below. N minus, no. n over n minus 1 beta n to the power n minus 1. We can obtain this kind of, but by using the Poelia formula, we can get this kind of lower bound. So the final if we admit this lemma and the change of variable by change of variables, recall that ZPX is equal to, okay, this one, UP epsilon PX plus XT divided by UPXT is equal to 1 plus TZP x to the power, this one. Therefore, this integral p to the power n minus 1 integral omega up to the power p plus 1x. Maybe I should change the letter y, dy, is equal to change of variable. This is also very elementary. Y is equal to epsilon px plus xt. Then dy is Jacobian epsilon p to the power n dx is equal to Pn minus 1 epsilon p to the power n, and here is this is upxp to the power p plus 1 integral omega will be changed to omega p and 1 plus p zp x to the power p plus 1 dx. Is right. This is the change of variables. And by the definition, this is equal to upxp to the power n. This one. So, and by theorem 1, the left-hand side goes to theorem 1 implies limit t tends to left-hand side is just equal to n over n minus 1 e beta n to the power n minus 1. On the other hand, limit sup right-hand side is equal to limit sup upxp is a L infinity norm of up. Therefore, this is up L infinity to the power n, and by this part, and this is Rn or Rn plus. But anyway, e to the power z dx. And by the lemma, this is bounded by n over n minus 1 beta n to the power n minus 1. So this is the lemma. Therefore, this e to the power n minus 1, it bounds this. That's why we get e to the power n minus 1 greater than or equal to limit sup up infinity omega to the power n. This is the end of the part of proof. Anyway, there are still many problems are open. So we want to proceed more to other type of equations which behave which have the blow-up behavior, which is known for Laplacian case or N Laplacian case, and we get some new result on the Finsler Laplacian case. Thank you very much.